Okay, so we are going to take thermodynamics 2, and we start with a little bit of mathematics, things you would have seen in differential equations and multivariable calculus. Now, what we are starting with is we are seeing that we have z, which is a function of x and y. If we have an expression this way, a function in terms of two variables, and we want to find the z, that's the total differential of z. The expression is what we see over here by equation 1. And the way we go about it is that we are looking at the way z is going to change with respect to x when we are keeping y constant. So that's for the first part here. And we're looking at how z is going to change with respect to y when we are rather keeping x constant. So the way we go about it is that we keep one variable constant and find how z changes with respect to the other variable. That's why it's a partial differential. We are not doing it for the entire thing. We are keeping one thing constant and then varying z with respect to another thing. Right. So the way we go about this is, if I want to find dz, it's going to be del z del x. So how z changes with x, right? When I'm keeping y constant, and I multiply it by the total differential for x, plus how z changes with y when I keep x constant and I multiply it by dy. Now what we can do is that we can actually write this in the differential form. So the expression here, I can represent it with m, and the expression here with n, so that I have m dx plus n dy. Okay, so m becomes this and n becomes that. The reason why we want to express it in terms of m and n is because we want to look at what we call exact differentials, right? And remember from differential equations that for your differential to be exact, then del m del y at constant x should be equal to del n del x at constant y. Or what we are basically saying is that, remember we said m was del z del x at constant y. Now I want to take that whole expression again, and this time I want to express it when I'm looking at y changing and x rather being kept constant. Initially I was looking at m as when x was changing and y was kept constant. Now I want to look at what happens even further. So after I've done the change in this form, what happens if I rather keep the x constant and change the y for that same m expression? So I'm now going to make it del m. This time, instead of me looking at the change in x, I always look at the change in y while I'm keeping x constant. And the same thing goes with n. So n was del z del y at constant x from the previous slide. And once again, for n, we got n by looking at how z was changing with respect to y when I kept x constant. So I want to see what happens even further. So after I've done this, what happens if I now find the expression when I'm rather changing x and keeping y constant? Now, if the two expressions, as we see here, are equal to each other, then we have what we call exact differentials, right? And exact differentials, we can actually, if we want to take it from the basis, from the basic part entirely, then it means that we are going to have our expression in this form. So I'll actually express it this way so that you understand what I'm talking about. Let me clear the screen up a bit. Okay. So what we are saying is, from here, if I take the expression here, right, del m del y. So m we said was del z del x at constant y. If I want to find del m, it means I can put my del here, and it is with respect to change in y. So that's del y. So I can bring my del y down here, right? For this whole expression, when I'm now keeping x constant. So what's going to happen is that this expression now can become del squared z, because I have my del here and then another del, and I'm finding del of del z, so it becomes del squared z, right? And for the base, I'll have del y del x. So that's what we have over here. Then I can do the same thing for n. So n we said was del z del y at constant x instead. So if I want to find del n, what I have up here is going to be del of the whole expression. And then once again, with respect to my change in x, when I'm keeping y rather constant. So in the same way, once again, I have my del of del z, which would be del squared z. And then I have del x del y. So the base becomes del x del y, which we have over here. So that's how we go about it. So it's just going to be the second derivative of z with respect to x and y is the same as the second derivative of z with respect to y and then x. So this is y first and then x. This is x first and then y, right? The second partial derivative. Let me be a bit more specific. So yes, that's how we go about it. And when we have these expressions, we see that they are when they are equal to each other, then we say that they are exact differentials. So we can take this as an example in thermodynamics. So we have U, our internal energy, as a function of entropy and then volume, right? So we said that if we want to find du, we are going to look at the partial change in u with respect to s when I'm keeping v constant. So with respect to the first variable, when I'm keeping the other constant, plus how my u is going to change with respect to v now when I'm keeping s constant, times the change in v. So this is the expression we are going to get. Then if I want to check for exactness, I can take this part here. Initially I did it with respect to s, so I'll now do the whole expression with respect to v now. So I'll have the del u del s, and I'm going to do it as del v, right? Initially was with respect to s, and I want to do it with respect to v. So I'm going to have my del 2u del v del s, which we have um yes, which we can see over here. Yes, that's it. Which we can see over here. Then we can do it for this side as well. So I can this was with respect to a change in v. So I can now make it with respect to a change in s instead. So that this will give me my del 2u del s del v, which we have over here, right? So that's what the expression is going to be. So we have these two expressions being equal to each other, and all of that is also equal to these two expressions over here. I think what I did was I actually switch the positions for this and this, but at the end of the day you get the same expression. I mean, I should have written this term here at the other side for it to be equal to like the notation I've done here, because this one is actually equal to this term. It's equal to the first term here. So, but it doesn't really matter. It's the same thing we get at the end of the day because they're all equal to each other. So you can just put that aside. I mean, what we're talking about is fine, right? So this is something that we need to keep in mind. And you might be wondering, so what happens to the constant portions there? We can decide not to include them in the notation. That's if we want to write it in a shortened form this way, and it's okay, right? It's fine if we do it that way. Okay. So now we want to start deriving some expressions that we'll be using throughout this course. So we can start with this example, or in fact, we are actually building up on what we started with. So we initially started with z as a function of x and y, and we said that from this it means that dz is equal to del z del x at constant y dx plus del z del y at constant x dy. Now what we want to do is that we want to now make x a function in terms of z and y. So we'll have the x to be equal to del x del y when we keep z constant times dy plus del x del z when we keep y rather constant dz. So it's the same understanding. The reason we are doing this is because we want to actually get an expression, and you see in thermodynamics this is actually valid because we can have a case where maybe we are expressing pressure in terms of sorry we are expressing pressure as a function of temperature and volume, right? In the same way we can say that temperature is also a function of pressure and volume, so we can actually express all of them in terms of the others. Okay, for example, I can have my pv is equal to rt for the ideal gas equation considering 1 mole of a gas. So I can express my pressure as a function of temperature and volume, or I can express my volume as a function of temperature and pressure, right? So all these things are valid. We can write them in all these ways. So initially we express z as a function of x and y. Now we're expressing x as a function of z and y. So we have this first equation we came across, and then we have this equation now, the expression for dx. Now what we can do is that okay, what we can do is that we can replace the dx we had from equation 1. Oh no, sorry. Yes, we can put equation 1 in equation 3. So equation 1 gave us the expression for dz, right? We can replace this dz here with what we had from equation 1, which is this one over here, the dz expression, right? So we can change the dz in equation 3 with that. We can replace it with that. And when we do that, what's going to happen is that this first part is going to be the same. So that's what we see down here, right? Then we'll have this part also coming down here. But then the dz, we have expressed it in this form now, the form that we expressed it as earlier. So we can actually expand. So yes, this was equation 4, what we had when we replaced the dz with the expression, right? So now if I expand, this term will multiply this term to give me this term over here, and then because it's a bracket, this term is also going to multiply this term to give me this term over here. So you can actually take your time and write it out so that you can also follow, right? Now I want to group everything with x on one side and everything with y on the other side. So the expressions with x, are this and this. So I can make it dx minus this expression over here to give me this side over here. So once again, you can actually take your time and write it out so that you can follow what we are doing. Then the dy terms are left, so it will end up being this plus this. So that's what we have down here. Then we can just bring our dx out so that it becomes 1 minus this expression we have down here, and then bring our dy out so that it becomes this expression we have down here. Now from that point, what we can do is that we can send everything to one side of the equal to expression so that it all becomes equal to 0, and you would understand why we are doing this in a bit. Now you'd realize that we were looking at varying x and varying y, and we said if we are varying x, we can keep y constant, we can vary y and we can keep x constant. So there's something we call or there's what we call varying it independently, right? If we are varying the terms dependently, it means that as we are changing x, y is also changing, because x and y are actually depending on each other in a way, right? For example, if I'm changing the temperature of maybe a gas system, it's very likely that it's to actually be affecting the volume. Do you get it? But what we want to do right now is that we want to say that okay, we want to change temperature, but we are ensuring that the volume is kept constant. So maybe I'll be working with a rigid volume. Like I'll assume I'm working with a rigid volume, so volume wouldn't be changing in that case. So the moment I do that, it means that if there's a dv, because I'm not changing volume, it becomes equal to 0, and it's just my t that I'll be changing, right? So this is independence variation. The moment it's dependent, it means that when I change t, v is also going to change because they are dependent on each other. That's dependence variation. But if you're looking at independence variation, what we are saying is that I can change t, but I'm going to keep v constant, right? So even in this expression, what happens if we vary the x and y terms independently? Now what's going to happen is that if, let's say, I want to vary x, right, it means I'm going to keep y constant. That's for the independence variation. It means I have to keep y constant. So if y is constant, then I won't have a change in y, so that becomes equal to 0, and it means that this whole expression will go to 0, right? In the same way, if I want to rather keep, or if I want to rather vary dy, it means that I have to keep x constant, so I can't have a change in x. The x becomes 0, so it means that this whole expression here goes to 0. So that's what we are coming to do. So we are seeing that in cases like this, we realize we are varying x and y, so that would be the x and the y. If you are varying them, we'll have a change in their values. We can vary x and y independently. So if we vary x, we must keep y constant, and then the y will be 0. If we vary y, then we must keep x constant, and then the x will be 0. So this is the expression we had. Now we want to look at what happens if we are varying y. So the x is 0. So it means that this expression, all of this goes to 0. So I'll just be left with this part of the expression. Now if this is equal to 0, remember we are varying y, so the y cannot be 0, right? So for the expression to be equal to 0, then it means that everything here in the brackets rather has to be 0. So basically all I'm saying is that if I have ab is equal to 0 and I know that b cannot be equal to 0, the only thing that can happen for the expression to be 0 is that a has to be equal to 0. So now we are saying that we were varying x and y and we kept x constant, so the x went to 0. because we are varying y, the y cannot be 0. So it means that for the expression to be 0, what I have in the bracket has to be equal to 0. So that's what I have down here, this expression down here, right? And would come back to equation 6 very soon. Now in the same way, if I want to rather vary x, right, it means that I won't have a change in y, so dy becomes 0, and this part of the expression goes to 0. So what I'll have now is I'll have this term here being equal to 0, being equal to yes, 0. What's at the right hand side here? So it will be this expression being equal to 0. And once again, we are not keeping x constant. We are looking at what happened when we varied x. So the x can be 0. So it means that everything in the bracket rather has to be equal to the 0. So that's what we have for equation 8. Now from equation 8, I can send this part of the expression over the equal to sign, so it becomes equation 9a, right? Then what I can do is that I have here del x del z are constants y, del z del x are constants y. So I can set one of the expressions to the other side of the equal to sign, so that I have del x del z are constant y being equal to 1 over del z del x as constant y. So this is an important expression we need to take note of, equation 9b. So what it's saying is that if I have del a del b at constant c is equal to 1 over, if I write the inverse form, so del b del a rather at constant c, right? Or I could have written this as del b del a at constant c then inverse, right? So that's what we are just trying to say, that with the differential forms you're working with right now, if I have del x del z are constant y is the same as 1 over del z now at the top instead of at the bottom here, and then del x now at the bottom instead of at the top here, but then still with the same like that same expression. So we have this expression for equation 6. Now I can send this part here over the equal to sign, so that I have the expression in this form now, right? And I can divide through by that value. So when I divide through, I'll have the left hand side being divided by that expression, right? And then the right hand side also divided by that expression. So this was supposed to be over um del x del y at constant z. So sorry, I didn't bring that in. So it's supposed to, both left and right hand sides are supposed to be divided by the same expression. So this expression divided by itself will give me the negative 1, because there's a negative here. It will give me the negative 1. And what I'm going to have for the left hand side, I'll have what I have at the numerator, so that's what I have here, but the denominator is going to become this inverse, right? And remember from what we said from equation 9b, the expression that we said was important and we shouldn't forget, it means that if I have the inverse here, I can just switch the positions of the x and y, so that I have rather del y del x as constant z, right? So this expression is what we call the cyclic equation, right? So we had del x del z at constant y times del z del y at constant x, and then we had del x del y at constant z inverse. So because it's the inverse, we have to, as it were, reciprocate. So I can switch the positions of the x and y and make it rather y and x, right, being equal to my negative 1. So this is what we call the cyclic equation. Now that's for finding this expression. What we can do is that we said it's cyclic, so I can have my x then going to my y to my z, and my z to my x. Yeah, so what we can do is we can take it this way. So I can start with the x, so I can say that del x, then the next term, so I'm going this way, del z at constant y, so I'm going this way now at constant y. I can open up another bracket, so I'll start from z now, so del z, then to the next expression del y, to the next expression at constant x. Then I'll now start from y now, so del y del x at constant z. So I'm just going around, right? It's equals negative 1. Or if you would, you could do it this way also. I think this one is better. So I'll start with x. So from x, I'm going to z. So del x del z. And then from z, I'm going to y at constant y. So I ended at y. I can start from y now. So del y, from y, I go to x. Del x, from x, I go back to z at constant z. So now I ended at z. I can start from z. So del z, from z, I go to y. Del y, and then from y, I go back to x at constant x is equal to my negative 1. Oh, I think it wouldn't show. Is equal to my negative 1. So it's the same expression. So you see that del x, del z are constant y here. You see that del y, del x are constant z here. And then you see that del z, del y has constant x in the middle here. It's equal to negative 1. So it's the same expression. You can use this if you need to recall. But mind you, okay, well, yes, this is the expression. So you can use this format to go about it. Okay. Now, let's take an example from Shom's outline of thermodynamics. So that's where we are getting most of these things. Now, we want to estimate the change in the specific volume of air, assuming an ideal gas. I want to use the differential form for dV. Right, so we're looking at a change in volume. So we're looking for dV. Now, we've been told that if the temperature and pressure change from 25 by 1 to 2, 25 degrees Celsius and 1 to 2 kPa to 29 degrees Celsius and 120 kPa. So we see that we are looking at volume, but then we want to find a change in volume when we have a change in temperature and a change in pressure. So it means that we are looking at volume as a function of temperature and pressure, right? So I can write my dV as del V del T. So when I look at how v changes with respect to t when I keep p constant times dt. So that's our first expression here. Then plus how v changes with respect to p when I keep t constant dp. So that's the second expression we have down here. Okay. Now we want to use the okay, they said using the ideal or assuming ideal gas. So we are going to use the ideal gas equation for 1 mole of a gas. Consider 1 mole of a gas. So we know that PV is equal to RT. But mind you, in our expressions, we have del V del T. It means we want to see how V changes with respect to T. Or how V, we also have del V del P. So how V changes with respect to P. So since we're looking at how V changes with respect to other parameters, we need V to be the subject in our expression. So we can say that V is equal to RT over P. Now, if you want to look at how V changes with respect to one term, remember it means you have to keep the other term constant. R is already a constant, right? So now let's try this out for del V del T at constant P. R we said is a constant. If I keep P as a constant as well, then R over P is a constant, right? So if I want to differentiate V with respect to just T, but it's multiplying a constant, what is going to be left is just that constant. So I'll end up getting R over P. And it's working on this kind of principle. So let's say I have y is equal to 2x. 2 is a constant. If I want to find dy dx, right, because 2 is a constant and I'm doing it with respect to x, I'll be left with just that constant. So that's the understanding or the analogy we are using over here. So what we are saying is that R and P are now constants from this expression. Right? I'm keeping P constant because I want to find this expression at constant P. So R and P are a constant multiplying my variable term. So if I look for the change in V with respect to that term, that variable term T, I'm going to be left with just the constant expression. That's R over P. Okay. If it was T squared, you use your normal relations. So if it was, this is just an example. If this was RT squared over P, right? R over P is a constant. So I can just say that maybe I'll represent it with C as a constant. So CT squared. So if I want to find my del V, um, yeah, so where my C is representing my R over P. So if I want to find how my V changes with respect to C, so with respect to T, I'm going to make it 2CT, right? As though it was, let's say, a constant times x squared. I would have brought the 2 down to multiply the whole expression. And I would have reduced this by 1. So I'll have just x. So that's the so it's like we are doing a normal differentiation, but the difference is that we are keeping one term constant and we are doing the differentiation with respect to the other term. So you need to be conversant with how to work your way around partial differentials, because you will really need it as time goes, especially if the equation of state is not the ideal gas equation. It might become a bit more complex, right? So the expression for del v del t at constant p, we said is r over p. So I can replace that here. So I'll have r over p dt. And I can do the same thing for how it changes with respect to p instead when I keep t constant. So once again, I have my V being equal to RT on P. I want to look at what happens when I keep T constant and rather change P, right? So I can write this as RT P to the power minus 1. Now, R and T are a constant, so I'm not going to worry myself there. So if I want to find how V changes with respect to P, as I can bring the differentiation with just P, considering the rest of them constants. So I can bring the negative 1 down. So negative 1 times my r times my t, then p to the power minus 1, and I subtract 1 again from it. So I have minus 1 rt p to the power minus 2, or minus rt over p squared. So that's what I have over here, times dp, right? And once again, if you want to make it easier for yourself, you can decide to represent rt with c. So I know that oh, this is a constant. I'm not doing my differentiation with respect to that term, right? Okay. So if the need be, you would have to practice um partial differentials, right? It's you will need it in this course. Okay. Now, this is the expression we are going to get for del v, right? Sorry, for dv. This was supposed to be d, not del. This was supposed to be dv, because we said that dv is going to be del v del t at constant p, and then everything else we've spoken about. So it's dv, not del v. It's a total differential, not a partial differential. So I can find my dv now. The question was asking us to find dv by putting in the values of r, t, and p into this, right? After I do my integrations, because I still have my dt and dp in there. Okay, so I can find my values. Now realize something: when we are dealing with small changes, this is going to be very accurate, right? So look at, they are changing from 122 kPa to 120 kPa. That's a small change. So this is very, very accurate to model that. They're changing from 25 degrees Celsius to 29 degrees Celsius. And remember, we'll be working in Kelvin. So if we're supposed to um yes, just keep in mind we'll be working in Kelvin. So the change is still going to be about 4 Kelvin if we should compute it. So we'll have here 25 degrees Celsius in Kelvin is going to give me 298.15 Kelvin. I'm adding 273.15, and then the 29 degrees Celsius would end up giving me, I think, 232.15. Yeah. Hey, sorry, 302. Forgive my math. 302.15. So if I find the difference in them, I'll have 4 Kelvin, which is not so large, right? So when I have very, very small changes, this expression really models that well. The dv expression models that very well, right? So um good. So I was also asking, so realize that we've been given two temperatures and two pressures for this for this question, right? So which ones are we going to fit into our expression? So all we are going to do is that we would have to put in the average value. Integrate over here, find maybe so the average temperature is going, we are using, if we use r at 0.287, So we can do is we can use the R as 0.287, so we can get an answer in meter cube per kilogram. If we used 8.314, we'll get it in meter cube per mole. So we can substitute all those expressions in there. So the T I'll have here is going to be the average T, and that should give us the value we are looking for. Okay. And there's something I have to talk about over here. I would confirm that and then um talk about it before I do the next video. So I'll come back to this point and then address something here before I do the next video. But we are saying that dv is once again it's supposed to be dv. So dv represents a small differential change in volume, and then when we have our delta, the one with the triangle, right? Delta v is a finite change, so we usually calculate it with final minus initial. And when our delta v is very small, as in the points at the final state are not too far from the points at the initial state, like what we saw in the question, we can use it to approximate our dv, right? So um we can use that expression here. So once again, my v is equal to rt over p. So the delta v is going to be rt over p at the final state minus rt over p at the initial state. I can put in the expressions, the value. So this will be t2, this will be p2, this will be t1, this will be p1. And when I do that, I should end up getting this expression. So as I said, I would confirm something at this point for the next slide. But then this is the general principle behind what we are working with or what we are doing. Okay, this is a general understanding behind it. Okay, okay, sure.